Welcome back to the Qualified Expert series from Subthesis. The standing reminder, this course is education about the expert determination pathway, not a certification, and nothing here is legal advice. Module 3 begins now, and the training wheels come off, because this is where the statistics start. Do not worry if you are not a statistician yet. Everything today is taught from first principles, on a table of 10 rows small enough to hold in your head, and every number you hear is one you could compute yourself with a pencil. Subscribe if the series is serving you, and the rest of the series lives at subthesis.com. Nobody's name needs to be in a dataset for the dataset to name them. That is the single most important fact in this field, and today we make it arithmetic. In Module 2, you learned the 3 lenses: replicability, availability, and distinguishability. Now we build the machinery underneath the third one. You will learn to classify every field in a dataset into 4 buckets, to compute by hand the exact number of possible combinations those fields allow, to group records into equivalence classes, to compute the number k that measures how well each person is hidden in the crowd, to spot the records that are unique on tiny subsets of fields rather than on all of them, and to respect the difference between being unique in your file and unique in the world. And we do it on a table you will live with for the rest of this course: 10 fabricated patients from a fictional Springfield hospital extract. 10 rows, 8 columns, no real people. By the end of today, you will know precisely which of those 10 records could be picked out of a crowd, exactly why, and what an estimator would have to do to tell you whether that matters in the real population. 4 objectives today, and each one is a thing you will be able to do, not merely recognize. First, you will be able to classify every field in a health dataset using the standard taxonomy from the National Institute of Standards and Technology: direct identifiers, quasi-identifiers, sensitive attributes, and non-identifying attributes, and you will know how the 2 governing NIST documents differ in how they carve that taxonomy up. Second, you will be able to compute the combination space of a quasi-identifier set, build equivalence classes by hand, and read off the value k, which is the seed of every risk metric in this profession. Third, you will be able to contrast sample uniqueness with population uniqueness, explain which one an adversary actually exploits, and describe at an intuition level how the Zayats and Pittman estimators bridge the gap between them. And fourth, you will have a repeatable decision procedure for classifying fields, including the ugly places identifiers hide: free text, metadata headers, derived codes, and rare dates, so that no schema ever fools you again. We finish by running that procedure on screen, at a pace you can pause and follow. Let us start with the taxonomy. Every engagement begins the same way. You walk the schema and put every single field into one of 4 buckets. Bucket 1, direct identifiers. These name a person all by themselves: names, social security numbers, medical record numbers, exact street addresses, telephone numbers, email addresses, biometric templates, and full face photographs. 1 field, 1 person, no ambiguity. Bucket 2, quasi-identifiers, also called indirect identifiers. These identify nobody alone, but combine into a fingerprint: age, sex, zip code, dates of service, race, ethnicity, spoken language, and rare or visible diagnoses. The formal definition is worth memorizing. A quasi-identifier is a field representing background knowledge about the patient that an adversary could plausibly already hold or could obtain from outside your walls. Bucket 3. Sensitive attributes. This is the payload, the thing worth protecting. Diagnoses, treatments, laboratory results, genomic sequences, and billing amounts. They rarely help identify anyone. They are the harm if identification succeeds. Bucket 4. Non-identifying attributes. Fields that neither identify nor injure, such as a randomized trial arm assignment or a broad facility characteristic. Two things make this genuinely expert work rather than clerical work. First, the buckets are not properties of a field. They are properties of a field in a context. A diagnosis is usually payload, but a rare and visible diagnosis in a small town is a quasi-identifier because the neighbors already know. That is, Module 2's availability principle wearing a taxonomy hat. Second, this classification is a written, load-bearing commitment. It goes into your report. Every equivalence class, every risk number, and every transformation downstream inherits it. Misclassify one field as non-identifying when it is really a quasi-identifier, and every number you compute afterward is wrong in the direction that favors release. Reviewers know this, which is why the classification table is one of the first things they read. There are two NIST documents everyone in this field names, and candidates routinely blur them together in interviews. Do not be that candidate. Interagency Report 8053, De-identification of Personal Information, published in 2015 under Simpson-Garfinkel, is the theoretical survey. It defines the terms, it catalogs the published re-identification attacks, and its central intellectual move is to insist that the boundary between an identifier and a harmless attribute is not fixed. It depends entirely on what auxiliary information an attacker can reach. IR 8053 will tell you that any attribute could, in principle, act as a quasi-identifier. That is a mathematically honest position, and it is also an unusable one for someone who has to ship a dataset on Friday. Special Publication 800 to 188, De-identifying Government Datasets, Techniques and Governance, is the operational companion, and it solves exactly that problem. It is prescriptive. It says direct identifiers come out irreversibly. It says the technical work is the systematic transformation of quasi-identifiers. And critically, it wraps the whole thing in governance, a disclosure review board that decides, on the record, which release model applies: public release, restricted access, or a controlled enclave. So the difference is not a disagreement, it is a division of labor. IR 8053 explains the mathematics of risk. SP 800 to 188 tells an organization who signs, under what procedure, and against which release model. For your practice, the discipline is simple. When you write that you applied a generally accepted method, name which document you drew the method from, and if you adopted the governance structure as well as the technique, say so. A reviewer reading your report should be able to tell whether you borrowed a definition or borrowed a whole process. Why do a few innocent demographics deserve so much fear? Because of what happens when they combine. In health data, the working list of quasi-identifiers is short, and you should be able to recite it. Age, or better, date of birth. Sex. Geography, meaning zip code or any finer locator. Dates of service, admission, discharge, procedure, and death. Race and ethnicity. Spoken language, and rare or highly visible diagnoses. That is the canonical list from the disclosure control literature, and almost every health release you will ever assess is built from it. Now the nuances that separate a careful classification from a careless one. Dates deserve special respect because a date can carry public context that a demographic never does. A birth date is a quasi-identifier everywhere, but so is the date of a car crash that made the local news, and so is the date of a multi-organ transplant that happens twice a year in your state. Those dates are matters of public record for exactly one person. Geography deserves the same care because zip code is only the obvious form. Census block, latitude and longitude, distance to the treating facility, and even drive time from home all encode location. Language and ethnicity deserve care because in a homogeneous service area, a single uncommon value can be nearly unique on its own. And the list does not stop at structured columns. A physician's note that reads, "Patient is the mayor's brother-in-law," has just converted free text into the strongest quasi-identifier in the file, and no column-based rule will ever find it. Hold on to the shape of the idea. One field is a fact, 2 fields are a coincidence, 3 fields are a fingerprint. The next slide shows you exactly why 3 is the number. Here is the arithmetic that makes uniqueness the normal outcome rather than the surprising one. Count the distinct values in Springfield. 9 distinct ages, because 34 appears twice, and every other age appears once. 2 sexes. 4 distinct 5-digit zip codes, 62701 through 62704. Multiply them. 9 times 2 times 4 is 72. 72 possible cells for 10 records. That is more than 7 cells per record. Think of cells as boxes and records as balls thrown at them. Most balls land alone. This is the pigeonhole principle run in reverse. Pigeonhole tells you that crowding forces sharing. Here, there is no crowding, so nothing forces sharing, and in a moment you will see that 8 of our 10 records do in fact land alone. Now watch the arithmetic get worse, because it always gets worse. Add admit date as a 4th quasi-identifier. Springfield has 10 distinct admit dates, so the cell space multiplies by 10, from 72 to 720, while the record count stays at 10. 72 cells per record. The space of possible combinations grows multiplicatively with every field you add, while your record count stays exactly where it is. Scale the intuition up. 5-digit zip code has roughly 41,000 values. A full date of birth across a century has roughly 36,500 values. Cross those with sex and you are on the order of 3 billion cells against a national population of a few hundred million, which is about 10 cells per person. When published research reports that a large majority of Americans are unique on zip, birth date, and sex, that is not a shocking discovery. It is this multiplication. The famous attack that made the finding notorious belongs to Module 5. Today, you own the arithmetic behind it. Meet the Springfield Discharge Extract, the table we carry through Modules 3, 4, and 7. Say the disclaimer with me, out loud, every time it appears. This table is fully synthetic. Every row is fabricated. The zip codes are real Springfield, Illinois zip codes only so the geography feels honest. No real patient is represented. That habit of announcing synthetic status is not politeness, it is professional hygiene, and you should carry it into every teaching artifact you ever build. Now the contents. 10 rows. Each has a record identifier, an age, a sex, a 5-digit zip code, an admission date, a diagnosis with its ICD-10 code, a payer, and a length of stay in days. Let us apply the taxonomy from slide 4. Direct identifiers, none present. The identifier column, R01 through R10, is a plain record number assigned for this extract, not a transformation of a medical record number, and I will show you in a few minutes why that distinction is the one you must actually verify rather than assume. Quasi-identifiers, 4 of them: age, sex, zip5, and admit date. Sensitive attributes, 2, the diagnosis and the payer, because payer status carries socioeconomic and program eligibility information that people reasonably regard as private. Non-identifying, length of stay, with an asterisk we will remove later, because an extreme length of stay is itself an outlier signal. 2 teaching flags before we compute anything. Record R06 is 94 years old, and every age above 89 is its own identifier category under the safe harbor list, so that row is already flagged before we do any statistics. And admit date is a field safe harbor would strip entirely, which is precisely why an expert determination exists, to keep it and prove the keeping is safe. Now we compute, and I want you to follow the procedure rather than the result, because the procedure is what you will repeat on datasets with 50 columns. Step 1. Fix the quasi-identifier set and write it down. We will use age, sex, and zip5, not admit date, not yet. The set you choose determines every number that follows, so a report that gives a K without naming the quasi-identifier set has said nothing at all. Step 2. Sort the table on those 3 fields. Step 3. Group rows whose values agree on all 3. Step 4. Count each group. An equivalence class is exactly that, the set of records sharing identical values on the chosen quasi-identifiers. Walk Springfield with me. R01 and R03 are both 34, female, 62704, so they form one class of 2. Now the rest. R02, 36, female, 62704, alone. R10, 35, female, 62704, alone. R09, 33, female, 62703, alone. R04, 51, male, 62701, alone. R05, 52, male, 62701, alone. R06, 94, female, 62702, alone. R07, 28, male, 62703, alone. R08, 29, male, 62703, alone. Count them up. 9 classes covering 10 records, 1 class of 2, and 8 classes of exactly 1. Check your arithmetic the way I do. 8 times 1 plus 1 times 2 equals 10, and 10 is the number of rows, so nothing was lost. A record alone in its class is called sample unique. Say the Springfield headline out loud. 8 of 10 records are sample unique on just 3 ordinary quasi-identifiers. The class size has a name, and it is the single letter this entire profession is organized around. K is the number of records in an equivalence class, and when you speak of the K of a dataset without qualification, you mean the smallest class size anywhere in the table. Springfield's K is 1, 8 times over. Here is why that number carries meaning rather than merely being a count. Suppose someone knows a target's age, sex, and zip code and wants their row. They match those 3 values against the table. Whatever comes back is an equivalence class. If the class holds 5 records, they have 5 candidates and no way to choose among them, so the probability of pointing at the right one is at most 1 in 5. If the class holds 1, the probability is 1. That is the entire logic, and it is why the phrase you will use in writing is that the probability of correctly identifying a record within its class is at most 1 over k. Notice how carefully that sentence is worded. At most, not exactly, because an adversary might hold extra knowledge that eliminates candidates, and we break that assumption deliberately next video. Within its class, because k says nothing about whether the target is in the file at all. And notice the sentence stops there. It does not say what an adversary is likely to know, whether they know the target is in the dataset, or whether they are hunting one person or harvesting everybody. Those are 3 genuinely different adversaries, with 3 genuinely different formulas, and they are the whole subject of Video 8 in Module 4. Today, 1 over k, one class at a time. 2 habits. Always report the minimum k and the class size distribution, never just an average, because averages hide the exposed person. And always report the quasi-identifier set beside it. 2 experiments on the same table, and both of them change how you will read a schema forever. Experiment 1. Add a field. Take the 3 quasi-identifier set and add admit date. Every one of Springfield's 10 admit dates is distinct, so the one class of size 2 splits, and the table resolves into 10 classes of exactly 1. Every single record is now sample unique. That is the curse of dimensionality in a sentence. Each additional quasi-identifier multiplies the cell space and can only ever split classes, never merge them. Adding fields never makes a table safer. Experiment 2, and this is the one nobody expects. Remove a field. Drop zip5 and group on age and sex alone. R01 and R03 are both 34-year-old females, so they still pair. Every other record still has a unique age. 9 classes again, exactly the same 9 classes. Zip5 contributed nothing at all to separating these particular records because age had already separated them. Push it further. Group on age alone, and 8 of 10 records are still unique because 34 is the only age that repeats. Age is doing essentially all of the work in this table. That is a genuinely important operational lesson. Quasi-identifiers do not contribute equally, and the temptation to generalize every one of them uniformly is both lazy and wasteful. If age is the field driving uniqueness, then coarsening age buys you real risk reduction, and coarsening zip5 buys you almost nothing here while costing a geographic researcher everything. Measuring which field carries the uniqueness is how an expert decides where to spend utility. Run both experiments on every dataset you assess. Add fields to see how fast it fragments, and drop fields one at a time to see which one was actually load-bearing. Being sample unique on the full quasi-identifier set is ordinary. Being sample unique on a tiny subset of it is a different and much worse condition, and it has a name. Look at R06, our 94-year-old woman in zip 62702. She is unique on the full set of 3, like 7 other records, but check her on one field at a time. She is the only record in zip 62702, so she is unique on zip alone. She is the only record aged 94, so she is unique on age alone. 2 single fields, each isolating her by itself. In the disclosure control literature, a record like that is called a special unique, and the algorithm that finds them is SUDA, the Special Uniques Detection Algorithm. SUDA works combinatorially rather than probabilistically. Instead of estimating a global risk number, it enumerates subsets of the quasi-identifiers and asks, for each record, On how many minimal subsets is this record unique, and how small are they? A record unique only on all 4 fields together scores low. A record unique on one field alone scores high. The scores let you rank records by vulnerability and treat them individually rather than punishing the whole table. Why does this matter more than it sounds? Because it tells you which tool to reach for. Generalizing age into 10-year bands rescues a record that is unique only on the exact combination. It does not rescue a record that is unique on a single extreme value, because after banding, 94 becomes 90 plus, and she is still the only one. R06 is the record that forces suppression rather than generalization, and SUDA is how you would have known that before wasting 3 iterations discovering it. The general rule: outliers on single fields resist generalization and eventually demand removal. Now the distinction that separates professionals from amateurs, and the one most often botched in a report. Being unique in your file is not the same as being unique in the world. Take R10, our 35-year-old female in zip 62704. She is sample unique, the only such row among Springfield's 10. But that zip code contains a great many 35-year-old women. Someone who learns R10's combination cannot tell which of them she is. Her sample uniqueness is an artifact of our sample being 10 rows, not a statement about the world. Now take R06, 94 years old, female, zip 62702. At extreme ages, the population thins dramatically, and the number of 94-year-old women in a single 5-digit zip code may genuinely be 1 or 2. If it is 1, then sample unique and population unique coincide, and anyone holding that combination has identified a specific human being. So define the terms precisely. A record is sample unique if its quasi-identifier combination occurs exactly once in the released dataset. It is population unique if that same combination occurs exactly once in the underlying population. Population uniqueness implies sample uniqueness. The reverse is emphatically not true. And here is the asymmetry to memorize. Sample uniqueness is what you can observe. Population uniqueness is what actually gets someone identified. Every sample unique is a candidate. Only some of them are real. An expert who reports sample uniqueness and stops has reported the warning light, not the fire, and has almost certainly overstated the risk, which sounds conservative, but is its own kind of error, because it pushes you to destroy utility you did not need to destroy. The professional question is how many of your sample uniques are population uniques, and you cannot answer it by looking at your file. So how do you estimate a property of a population you cannot see? This is the central estimation problem in statistical disclosure limitation, and appreciate its shape before we name any estimator. You hold a sample. You can compute its equivalence classes exactly. What you want is a statement about the population from which those records were drawn, and you do not have the population. 3 ingredients get you there. Ingredient 1, the sampling fraction, meaning the proportion of the population your file represents. This dominates everything. If your file is the entire population, a census, then sample unique and population unique are the same thing, and there is nothing to estimate. If your file is 1% of the population, a sample unique probably has 99 invisible twins, and your observed uniqueness wildly overstates the truth. Springfield is the extreme case. 10 records drawn from the population of zip 3627, a sampling fraction so far below 1% that nearly every sample unique is an artifact of tiny sample size. Ingredient 2, external population counts. Public census and survey tabulations tell you how many people of a given age, sex, and geography exist at all. That is what anchors the estimate to reality, rather than to assumption, and you must cite the vintage of the tables you used, because populations move. Ingredient 3. A superpopulation model. This is the statistical machinery that assumes the finite population was itself generated by some underlying probability distribution, which turns an impossible counting problem into a tractable parameter estimation problem. The observable input to that model is the class size spectrum, the count of how many classes have exactly one record, how many have exactly two, and so on. Springfield's spectrum is 8 classes of size 1 and 1 class of size 2. That little vector of counts is what the next 2 slides feed into an estimator. The first estimator to know is the Zayats approach, developed by Laura Zayats at the United States Census Bureau around 1991, and its intuition is the one you will reach for most often because it is the one you can explain to a lawyer in 30 seconds. Zayats estimates the proportion of population uniques directly from the frequencies of equivalence classes observed in the sample, using the sampling fraction as the scaling lever. The intuition runs like this. If you release the whole population, every sample unique is by definition a population unique. So the conditional probability that a sample unique is population unique equals 1. As the sampling fraction shrinks, that probability falls because each unique you observe increasingly might be one of many identical people who simply were not drawn into your file. So the conditional probability that a sample unique is also a population unique rises with the sampling fraction and falls as the sampling fraction falls. Work Springfield through it. 10 records drawn from the population of a whole ZIP3 region. The sampling fraction is minuscule. Under the Zayats intuition, almost none of our 8 sample uniques would survive as population uniques, with the glaring exception of the record whose quasi-identifier values are rare in the population itself, which is R06 again. That is exactly the right answer, and notice you got there without heavy machinery. What Zayats gives you is speed and a defensible first pass, and what it costs you is precision, because it leans on a simple proportional relationship rather than modeling the full shape of the class size distribution. Use it as a screen. If the Zayats style estimate already says your risk is not small, you have your answer and you go mitigate. If it says the risk is borderline, you escalate to a model that takes the distribution seriously, which is the next slide. The Pitman estimator is the one to name when a reviewer asks how you estimated population uniqueness on clinical data, because it is the approach with the strongest validation record in exactly that setting. Here is the intuition without the algebra. Zayats used one summary quantity, the sampling fraction. Pitman uses the entire shape of your data. Recall Springfield's class size spectrum, 8 classes containing 1 record and 1 class containing 2 records. That vector is not just a curiosity, it is a fingerprint of how the population's diversity behaves. A population with enormous diversity produces a sample full of singletons. A population with a few common profiles produces a sample with a few large classes and a long, thin tail. The Pitman sampling formula, which extends the earlier Ewan's sampling formula from population genetics, is a probability model for exactly this: how a sample of n records partitions into groups of various sizes when drawn from an underlying population. You fit the model's parameters to your observed spectrum, and then you run the fitted model forward to the full population size to predict how many of your singletons would still be singletons if you had drawn everybody. Because the fit uses the whole spectrum rather than a single ratio, the resulting estimate of population uniqueness is markedly more accurate, and studies on real clinical datasets have shown it tracking the truth well where cruder rules do not. 2 practical notes. First, Pittman needs a credible population size, so you still owe the census or survey tabulation that supplies it, and you still cite its vintage. Second, and this is the part people forget, Pittman is estimating uniqueness in the population, not the probability that anyone actually attacks. Turning a uniqueness estimate into a risk figure requires an adversary model, and that is Module 4's job, not this slide's. Classification cannot be intuition because intuition is not reviewable. Here is a decision procedure you can run field by field and hand to a junior analyst. Question 1. How was this field generated? Not what does the header say, how was it made? If the answer involves any transformation of a real identifier, a hash, a truncation, a concatenation, or an encoding, treat the field as a direct identifier until someone proves otherwise with the generation code in front of them. Question 2. Could a person outside our organization plausibly know this value about a specific patient? If yes, it is a quasi-identifier. Neighbors know age and sex and street. Employers know absence dates. Social media knows almost everything. This question, and not your comfort level, is what makes a field a quasi-identifier. Question 3. Could this value be looked up in any external file that exists? Voter rolls, property records, obituaries, court filings, commercial data broker products. If yes, quasi-identifier, and note the specific external source in your worksheet because that note is what makes your reasoning auditable. Question 4. If this value were correctly attached to a named person, would it cause harm, stigma, legal jeopardy, or economic loss? If yes, sensitive attribute, and it belongs in the payload column. Question 5. Is this field an outlier magnet, meaning does it contain extreme values that will isolate a handful of records regardless of what you do to the rest? Length of stay, billing amount, and age all qualify. Flag those for the special uniques analysis, then the rule that binds the whole thing. Write the answer for every field with the reason into a classification table and date it. Undocumented classification is the single most common weakness in weak determination reports, and it is the easiest one to fix. Everything so far assumed that the schema tells the truth. It never quite does, and free text is where it lies most. Clinical narratives, discharge summaries, nursing notes, pathology reports, and radiology impressions are written by humans for humans, which means they contain exactly the details that make a person a person. Patient names, and worse, the names of relatives, employers, and referring physicians. Exact dates spelled out in prose that no date column ever captured. Occupations specific enough to be unique in a county. Addresses embedded mid-sentence. And relationship descriptions. Patient's daughter works at the plant, that are quasi-identifiers of extraordinary power and completely invisible to any column-based rule. The de-identification standard draws no distinction between structured fields and free text, so a clean header row proves nothing whatsoever about the file. Operationally, here is what the work looks like. You do not eyeball it because volume defeats eyeballing. You run a named entity recognition pipeline that tags persons, organizations, locations, dates, and identifiers, and you replace each tag with a generic surrogate rather than deleting it, so that downstream language models still see grammatical text. Then, and this is the step that gets skipped. You manually review a random sample of the output, and you count what leaked. Recall matters more than precision here, because a missed name is a disclosure, while an over-redacted word is only an inconvenience. 2 failure modes to watch for. First, misspellings and abbreviations defeat dictionary-based tools, and clinical notes are full of both. Second, the rarest content is the most identifying and the least represented in whatever the tool was trained on, which means your error rate is worst exactly where it matters most. Report the sampling method, the sample size, and the measured leak rate in your determination. A number beats an assurance every time. 3 more hiding places, and these are the ones that survive an otherwise competent de-identification. Hiding place 1, image metadata. Medical images in the DICOM format are not pictures, they are containers, and the container carries a header with hundreds of tagged elements. Patient name and patient identifier tags, obviously, but also study and series dates and times to the second, accession numbers, device manufacturer and serial number, institution name and address, referring and performing physician names, and free text study descriptions that clinicians use as a notepad. Worse, private vendor tags carry undocumented content that no published profile enumerates, and burned in text on the pixels themselves, ultrasound annotations especially, is invisible to any header scrubber. The operational rule is that you dump the headers of a random sample of actual files, compare against a published de-identification profile, and treat private tags as unsafe by default. Hiding place 2, derived codes. A study identifier generated by hashing or truncating a medical record number is a direct identifier wearing a costume. An unsalted hash of a short numeric identifier is trivially reversed by generating every possible input and comparing, which for a 9-digit space is seconds of computation. So the question is never, what does the column look like? It is, what was it made from, and who still holds the mapping? Hiding place 3, geography in disguise. Census block identifiers, exact latitude and longitude, distance to the treating hospital, and drive time from home all reconstruct location, and location intersected with public property records reconstructs an address. Build the permanent habit. Never classify a dataset from its documentation. Open the actual data, read the ugliest free text field, dump the metadata, and ask of every column what it was derived from. Your turn. Here is a 10-field schema from a hospital extract. Pause the video, write the 10 field names down, and assign each a bucket. I will give the answers in a moment. Ready. Here they are. Patient key, a 12-character string. The documentation calls it a random key. You ask how it was generated and learn it is the medical record number, truncated and hashed without a salt. Direct identifier, full stop, no debate. Date of birth, full precision. Quasi-identifier, and the strongest one in the file, because it alone carries about 36,000 distinct values. Zip5, quasi-identifier. Admit timestamp, recorded to the second. Quasi-identifier, and far worse than an admit date, because a timestamp to the second is nearly unique on its own. Provider NPI, the National Provider Identifier. It identifies the clinician, not the patient, so it is not a patient direct identifier, but for a solo rural practice, it encodes geography and specialty precisely, so classify it as a quasi-identifier and say why. Note text, free clinical narrative, unclassifiable until someone reads it, and until then, you must assume it contains every category at once. DICOM path, a file path to an image. The path itself may embed an accession number, and the file behind it carries the headers we just discussed, so it is a metadata carrier and stays unresolved until the headers are dumped. Lab A1C, a hemoglobin measurement, sensitive attribute, and a quasi-identifier at extreme values, because an A1C above 15 is rare enough to isolate. Trial arm, a randomized assignment. Non-identifying, one of the very few genuine members of Bucket 4. Drive minutes, travel time from home to the hospital. Geography in disguise, quasi-identifier. If you scored 8 or better, you are reading schemas correctly. 3 takeaways, and each one is a habit rather than a fact. First, classification comes before computation. Every field goes into one of 4 buckets. The boundaries depend on what auxiliary data exists outside your walls, and the classification is a written, dated, load-bearing commitment that every downstream number inherits. Run the 5-question decision procedure and hunt the hiding places, free text, metadata headers, derived codes, and geography in disguise. Second, the equivalence class is the atom of risk measurement. Fix the quasi-identifier set, sort, group, count, and read off K. Springfield gives us 9 classes, 8 of them singletons, a minimum K of 1, and the sobering discovery that age alone was doing nearly all the work, while adding admit date made every single record unique. The probability of picking the right record within a class is at most 1 over K, and everything beyond that sentence belongs to the adversary models in video 8. Third, sample uniqueness warns and population uniqueness burns. Census anchors and superpopulation estimators, Zayats for a fast conservative screen, and Pitman when the answer is close, bridge the file you hold to the world and adversary searches. And remember R06, unique on age alone and on zip alone, a special unique that no generalization will ever rescue. Next video, the toolbox that fixes all of this, and the price each tool charges. Video 7 opens the de-identification toolbox. 9 transformations worked on real numbers, the formal privacy models built on top of them, and an honest placement of differential privacy. Same Springfield table. Subscribe so it reaches you, and everything else is at subthesis.com.